off to a perfect start. My daughter's on trick or treat, go to jail Roblox. It's like she was trick or treating in the neighborhood caught on fire, and they tried to save somebody, and then they had to get put in jail. And then the laughing skeleton killed the police, and then she found the secret lever to open the jail bars, and now she's escaped and she's taking it on the lam. Roblox, right? Oh, you got tired of that? Oh, she's in. What game is this called? Escape from Obby?
Then I'm using the car.
Man, I would be nauseous in that car. Car has elliptical wheels, so I just like wanting to get things going here. Yeah, on this stream I have been doing some stuff on nuclear, and yeah, I guess I want to say a lot of people don't know what nuclear power is. I was at Georgia Tech when we were having a big public comment period on nuclear activities on the Tech campus. Uh, there were these guys in suits that were tech students, right? And like we're up there for the second day, and the guys in the suits that I thought were, I thought they were in engineering school or something like that. They finally said, "What is nuclear power?" Like, so, yeah, it's just like lighting a. You know how you light wood on fire and burn it, and then you boil water. That's what nuclear power is. You take, except you take something that's a metal, and when you put enough of the metal close to other pieces of that metal, uh, it gets really, really hot. And if it gets too hot, it explodes. That's why Chernobyl exploded, because it can get really hot really fast. So, and like nuclear scientists always says, it can't explode because we're scientists. Okay, it can explode. And I'm just as much a scientist. I have a Bachelor of Science from Georgia State University. I know it's very backward here in the South. Everybody knows that we're behind and stuff. Um, but yeah, a nuclear reactor can explode. Something can go wrong. Um, can overheat and melt as well. I think that's what happened in Fukushima. Like, okay, so when one of the things you do, have you ever had a bullet? Have you ever, like a slug? That's what we do with uranium, right? Is we make it in these little bullets and we put it in the tube. It's like a copper alloy tube. Um, so a nuclear fuel rod is like a copper alloy of some kind fuel rod. And you can look it up to see exactly what it is. But because it has uranium in it, there's radiation and neutrons and stuff coming out of it. And the neutrons can hit other nuclei, right? And if they're going at not too fast and not too slow, they can also split other nuclei. And that's called a criticality when you have enough uranium like that together. You say it's a critical mass, enough for a sustained chain reaction. But you have to bear in mind, yeah, it can explode. Well, say or melt. Now, like here's some scenarios. Say you put a bunch of uranium together and it melts, and it melts so hot it like you know spreads out. It goes over some big side is very thin or something like that. Then it's not likely to explode because you need it's gonna put out a lot of radiation, extreme heat, and vapors of chemical toxicity, and waves of gamma radiation, penetrating gamma wave radiation electron streams, which are called beta radiation, and then alpha particles, especially when the fuel rods
Alpha
themselves melt.
Alexa.
When the fuel rods themselves melt,
I
yeah,
said
it's all in the
Alpha
open air.
Alexa.
Yeah, cool. So, all a nuclear power plant does is it boils some water, and then the water pressure, like a steam engine. You've seen a steam engine before, or a turbine. So it's just like a steam engine. You heat up, you get some pressure, and use the pressure to drive a steam turbine. So it's not people. These nuclear scientists try to make it. It's really, really complicated because I'm a scientist and you're not. You can never understand.
So quiet
But
this one.
yeah, like think of it this way: when I have a decay of uranium atom,
But this is fun.
generally I've got three neutrons, which, according to how fast they're going and what they hit, um, could split other nuclei, causing a chain reaction. Right now, and if that was just like three split three, and they split three, it'd be like 3, 6, 9, 27, 81.
Are you screaming?
Turn 43. Right, all of a sudden it gets really large. Right, and you can put this on your calculator. Put 3 times 3 in your calculator and hit equal. Equal again. You do it a few times and your calculator breaks. It's just error.
Get behind your fence, buddy.
Swerve. I'm over there fighting with Swerve. That's my Twitch stream. But, so, like, when you get uranium, it's like not really concentrated. You have to do all this stuff to refine it and all this kind of stuff like that. To get your like a metal slug, like so heavier than lead. It's really heavy, and then stack that up in those tubes, and you get a really long tube, and that's a nuclear fuel rod. You put nuclear fuel rod assemblies together. Usually they're in big square assembly, and the neutron field gets a sustained reaction, and it gets really hot. Now that glow that you see is it's kind of like a blue glow or whatever. I believe that's polonium, which is a fission product. Now think about it. You've got uranium. It's a big, heavy nuclei.
I invited you.
You break it.
I invited you.
Fission. Split it, right? Gets hit by other neutrons. It gets split.
Dad, look.
Yeah, that's me.
I need a pot.
Okay, the potty's right behind the curtain. So
I need the wand. I need 2 wands.
you need 2 wands. She's got to have her magic wand when she goes to the potty. I'm gonna go take care of this because I need to wipe her butt. But I'll come back and I'll talk about what is a nuclear reactor and so on, some more in just a second.
Hold on down here. That's where you need to go.
serious environmental problems with nuclear power and nuclear weapons. Nobody wants to take the waste, right? Now, what happens is you've got uranium, which is all relatively innocuous. You could isolate yourself from it. It's like an ore in the ground, but instead of leaving it alone, you dug it up and we concentrated it together. Now you concentrate it together and you do this neutron bombardment stuff, right? Because when you concentrate it together, you get a criticality, it heats up. But the heat is coming from the release of nuclear energy, these nuclei break, it's releasing energy, and we have some basic ideas about that. Like we have this equation called E equals mc squared, which is the mass energy equivalence. Oh, wait a second. And you know what? Probably nothing I've said. You probably hadn't been able to hear anything I've said. Where did my... Oh, she's watching me play. That's awesome. Yeah. She went over to watch the stream. Yeah. Okay, so what I was talking about is like what I was at at Georgia Tech with some citizens groups back in the many years ago. I say in the 90s, the late 90s, and I didn't like that they were even operating a nuclear reactor. But not only did they have a nuclear reactor, they had a cobalt irradiator, which is cobalt 60, is an unstable isotope of cobalt, and it's got a half-life of about 5 years, and which means that it puts out some serious gamma wave radiation. It does not turn you into the Hulk. It kills you very quickly. Right? Even robots have trouble getting to it and close to it or whatever like that. Concentrate cobalt 60. I think that was the concentration of cobalt 60 for the creation of a radiator was actually done up in Augusta, which is in our state, and then somehow, some kind of way, they transported it across the state. Very seriously dangerous stuff, right? To bring it down the Georgia Tech campus for GTRI, and everybody in the neighborhood, the ladies or whatever, they were like, you know what? It's probably weapons research, right? That's why I have a cobalt irradiator. And I ran that by Arjun Makhijani of the Institute for Environmental Energy Research, and it was like, yeah, it's one of the things. Intense gamma radiation happens in a nuclear blast, and you have a problem with multiple warheads. Where if you have a warhead that's got multiple H bombs on it, and one H bomb goes off before the other ones do, how do you make sure that that other very expensive H bomb isn't disabled? Because it's got electronics and computing stuff in it, and you don't want it to be destroyed but it's very close. It may be very close to a thermonuclear explosion. So we were, everybody was talking about it. They were thinking that what was happening at Georgia Tech is they were taking electronics and they're experimenting with trying to make electronic devices that could withstand, that would still be operational through big electromagnetic pulse. She's watching me on stream. I'm glad I won some. She would be mad at me. Yeah, that's right. Yeah, I was practicing. See, that's what you do. See, Daddy didn't know how to play that before, right? Daddy didn't know how to play that game at all, and now he's doing pretty good. Well, I mean, not that great, but good enough that when she looks at a recording of me, she sees me winning and being the last man standing. When you come in the room, does it get harder for me?
Yeah.
Yeah, it does. Because I just want to hug you, but when I hug you, then the other robots blow me to smithereens, and I explode in tiny little pieces and burn up in a pile of vapor emanating molten slag. That's what happens. Here, let's have some delicious oatmeal. How is it, Chief? Is it good? But yeah, I want to go over it again. Like uranium fuel, right? You make these like bullets of uranium called slugs, right? You put them in this copper alloy tube, stack them all up, right? And then you seal the tube up because when you assemble them into a fuel assembly, you're going to get neutron bombardment, and everything's going to get more highly radioactive. And you want to keep that sealed inside a tube away from the water that's circulating through the reactor. So if suddenly you got a power surge or something in the base of the core, right? I think what was said about Chernobyl is that they have graphite rods. They're called control rods, and they shoot them when they scram, when they shut the reactor down for hit the emergency off switch or whatever, in an emergency, right? That inserts the graphite as far as it will go into the core. And there's a great at MIT. There's a nuclear power 101 course. I think it's MIT. And they really, I want to watch it again. They really explain very clearly all that we understand about how the RBMK reactor at the Chernobyl exploded. But I think it was VM Chernyshenko. He said it was a power surge because the graphite, when they're trying to absorb, the graphite absorbs the neutrons, right? So you don't want continued neutron bombardment when there's a danger of the reactor running off, right? Going off the scale or whatever like that. So they hit the emergency shutoff switch, and these graphite rods inserted as far as they would go in the reactor, but they weren't the full length of the core, right? So when they went all the way in, the idea is when the graphite passes through the bottom of the core, it's gonna solve the problem of neutrons. It's gonna absorb all the neutrons, and then the graphite rods not being the length of the core is not going to matter because all the graphite's going to pass through the bottom, and that's going to squelch everything, shut everything down. And then when the extenders are going through the bottom of the core, right? It will already be not a critical situation down there. But Chernyshenko said that when those extenders, when it was no longer graphite and the extenders were in the base of the core, there was a power surge, and the reactor exploded. Whoops. And scattered poisonous radioactive heavy metal toxicity crap over Europe and the world. Right. And Fukushima.
I got the sea.
Wow. Awesome. I haven't been over this in a long time, but basically, like in Chernobyl, what caused the reactor to explode was they hit the emergency off switch, the safety switch, the alleviate us from all danger switch, and when they hit that, the reactor exploded. Fukushima, they were like this huge reactor, it'll never run off because we got. But if the concern is like if the power went out, right, the reactor could get out of control if there was no electricity, right? Something happened, a storm or something like that. And they were like, well, we've got these big generators all around. The power goes out, the generators automatically kick in, and then that gets the reactor back under control, and we can shut it down, right? But there was a tsunami, and all the generators were suddenly underwater, and they didn't work. And the power went out naturally when there was a big tsunami or whatever. And then Fukushima exploded, the reactor exploded. Made a bunch of territory uninhabitable, right? And So yeah, a reactor can explode. It can melt. Okay, now I was talking earlier. I know that like say you have a fuel assembly and it melts, but it
I
spreads out.
finally got the sheep.
It's less likely
I
to burn
totally
to
got the
explode.
sheep.
Awesome! Look at those cool shoes you've got. They have wings on them. Wow, it's awesome. Um, yeah, nuclear power's pretty stupid. Solar and wind, yeah, are the way to go. And it's a lie. They say, oh, it's zero fossil emissions, and they look at a fuel pellet, and they'll hold up a fuel pellet, and they'll say one fuel pellet generates more energy than a barrel of oil or several barrels of oil or something. Like, that's really amazing. Yeah, but to get that fuel pellet, what did you have to do? Well, you had to dig up the ground. Well,
Do you wanna play
did
this
you do that
game?
with your
Dad, do you wanna
fingernails?
play this game? Dad, do you wanna play this game?
Sure. You want me to?
With me?
Okay. You need to eat your oatmeal, and then I'll play it. We got a few more bites, and I'll try to start Roblox here. Okay. Let's see. I'm looking for Roblox. Okay. Starting Roblox. Um. Yeah, let's see. Okay, the Roblox start. Okay, it's downloading a Roblox update. Okay. It's configuring a Roblox update. Come on, we got to eat this oatmeal so we'll be big and strong. You didn't eat enough food yesterday. I didn't drink enough water. I'm like,
Oh, no, back up.
you hear me? No, back up.
Really pissing me off.
How you doing? Okay, Roblox has been upgraded, as it were. Alright, so, and actually what I need to do is, I'm getting, drink some chocolate milk. Come on. Good. Yummy, yummy chocolate. Delicious. Chocolatey delicious. Oh, she's really drinking chocolate milk. So on the stream, I would like to. Okay, well, we'll wait a little bit and then we'll get back on it. Okay, so what I want to do here is just we'll start with uranium. What we're gonna try to make is uh,
Raccoons are my favorite animals. Raccoons are my favorite animals. Raccoons are my favorite animals of all.
they are.
Yeah.
Wow.
This one is Goldie.
Goldie. That's cool. Alright. Okay, I'm working on it. Yeah, sweet. Aw. Mm.
So annoying.
So annoying. So annoying.
Oh,
So annoying.
aren't you?
Wow, look at this. I'm kind of scrolling down and looking over the lay of the land, biotic, spasmodic, production and mining. Oh, this is all is interesting stuff. So we start with uranium. God. Uranium compounds. Wow, this is wonderful. Look, I mean, Wikipedia, here it is, man.
That's the second time he did that. Stop doing that.
Yeah, yeah. It's, I don't know if you could hear that or not. I was like yelling at my teammate. Of course, he can't hear me. So, you know, because he jumped out somewhere and blam, he got blown away, right? And then they did exactly the same thing. The same guy blew him away again. It's like, that's the second time you've done that. Stop doing that. You're gonna die. Wow, and the Wikipedia article has the notes. It's got uh, all the sources. Look at all that. Nuclear weapon design, Federation of American Scientists, archived from original. I love Federation for American Scientists, FASS. They had some arms control monitor. I used to be really up on that.
Here he comes. There's Morocco's team. He's got more power. What is that? They're trying to get me to buy that thing. 116,000 damage. Yeah,
Yeah, if you watch my Macarena stream, uh, yeah, I noticed that when they introduce a new weapon, all the bots have it. Yeah, that's a great idea because people are like, "Dang it, I need that," because they're getting killed by bots, right? I'm like, let me try to not get hit by that thing. That's a skill, right? That's something I can work on. I have control of. This is a great article. Just a great place to start. Okay, periodic table at the bottom. So theoretically, I hit copy, right? And I should have gotten a message from Text Aloud because Text Aloud is supposed to be running. It's not running.
Oh, that was my friend.
Yeah.
Oh, that was my friend. Oh, that was my friend, Dad.
No, really?
Yeah, you were
Okay, so
telling about my friend.
I think this, if you're watching the stream, this was the Savannah Riverside article. Now, one of the things that happens in nuclear reactors is I was talking about before I got interrupted. Um, so, is you get sort of I think it's it's an isotope of uranium U-235, which is you can make a devastating nuclear weapon with it, whatever, or you can make nuclear fuel with it. Oh, hug, thank you. But one of the things that happens is you get all this weird stuff when you have U-235 and you do a neutron bombardment, right? And all these atoms get shattered into little fragments or whatever. Generally, you get some unstable isotopes of various elements in the periodic table. They're a lot of times people say, these are not naturally occurring. What is the definition of nature? There is no nature, right? This happened. We did this, right? And not naturally occurring, but it's bad stuff, and we're a factor in helping it along to our own detriment or whatever. But when you change, what happens is a nuclear fuel rod becomes all these broken little fission products, it's called, which are just the shattered pieces of the atoms, which are generally unstable isotopes of various elements from the periodic table, and they have varying levels of stability. If they're extremely unstable, they have a shorter half-life. That's a half-life is the amount of time it takes for half of the radioactivity to be dissipated, and generally there's a decay chain that your isotope that you're dealing with, of whatever element it is, it decays into something, and then that is unstable and it decays into something, and it's actually a pretty complicated process, but it's like broken stuff. And what I'm getting to, and we'll get to this later, is plutonium. One of the things that happens with these nuclear fuel assemblies is plutonium is produced, right? So the plutonium is it's fissionable, but better than that nuclear weapon in the mind of somebody making a nuclear weapon or a thermonuclear weapon. Plutonium is awesome because it's fissile. It's so it's spontaneous. You get a criticality with plutonium, and you immediately get a fire, an explosion. It's more explosive, let's say. So you got better chances of getting a bigger yield, right? Now you measure the yield in kilotons, right? But remember this. Just remember 4E12, because generally, like you want to, when you got a kiloton yield and you want to do E equals mc squared, right? Generally our energy is in joules, right? Now a kiloton is many joules, so the conversion factor is, I think, 4.184 E12. And oftentimes when I'm doing a calculation like that in my head, I'm looking at a nuclear weapon, say, and then they say, well, it was so many kilotons or so many megatons, right? Well, if I want to convert that to joules, I'm going to multiply it by a massive conversion constant. There, 1 kiloton is 1 kiloton is equal to 4.184 times 10 to the 12th power, which I'll just say 4 times 10 to the 12, or 4 with 12 zeros, right? What is that, 4 trillion or something like that? So you take however many kiloton. Well, since you've got an equality like that, if you've got a kiloton amount, say you've got Hiroshima's bomb, I think it was 15 kilotons. Well, you take your equation, 4.184 E12, or just 4 E12, right? What is that? That's joules, right? Is equal to 1 kiloton. So you divide that equation, both sides, by 1 kiloton. And on the right-hand side of the equation, you've got 4.184 E12 divided by 1 KT, kiloton, right? And then on the other side, you got 15 kilotons. Well, the kilotons cancel out, and you go 15 times the 4.184, or I'll just say 4, is going to give you 60 E12 joules, or 6 E13 joules of energy. It's huge. Like your Matt, that's like your. We do watts. I think watts is, and I could be wrong because I forget stuff sometimes. But watts, I'm pretty sure, is like joules, the amount of energy per second, right? So 2,500 joules per second is like what you get from a gas stove, if I remember, right? Let's see. She's playing piano. It sounds beautiful, dear. Keep practicing. You got to practice every day. And see, I put Roblox on update, and it's supposed to run, and it didn't run. Hold on. Scary. I'm trying to. It's saying it's starting Roblox, so we're gonna find out. Will Roblox crash again? I don't somehow. Okay, so theoretically now, right? If I go back here and I just put my mouse over this Wikipedia article, right, and right click somewhere there's not a link, I can select copy. Okay, this is my article on uranium, and to make this a productive day, Roblox is starting, right? We're going to learn about uranium. But while we play Roblox, right, we'll learn about uranium. All right, let's see. All right, so here, I don't know if let's see what my Streamlabs is saying. Bring it up front. Don't tell me Roblox crashed again. Great. Maybe I need to download and reinstall Roblox. But what I'm trying to get to is I'm trying to get to the point where I play this file. So.
Uranium is a chemical element with symbol U and atomic number 92. It is a silvery gray metal in the actinide series of the periodic table. A uranium atom has 92 protons and 92 electrons, of which 6 are valence electrons. Uranium radioactively decays by emitting an alpha particle. The half-life of this decay varies between 159,204.5 billion years for different isotopes, making them useful for date.
Now I got my layout. Let's see.
The most common isotopes in natural uranium are uranium-238, which has 146 neutrons and accounts for over 99% of uranium on Earth, and uranium-235, which has 143 neutrons. Uranium has the highest atomic weight of the primordially occurring elements. Its density is about 70% higher than that of
one
lead,
bite.
and
It's almost
lower
done.
than that of gold or tungsten.
Good.
It
It helps
naturally
you
in
grow
low
faster, dear,
concentrations
when you
of a
eat.
few parts per million in soil, rock and water.
Don't you want
and
to
is
grow faster and be a big
commercially
girl
extracted
and
from
not be a little
uranium-bearing
kid?
minerals
Right?
such as uraninite.
You gotta try to eat your oatmeal. Drink some
Many
chocolate milk.
contemporary uses of uranium
Don't want it?
exploit its unique nuclear properties.
Would you like some delicious Cheerios? I'll have some.
Uranium-235 is the only naturally occurring fissile isotope, which makes it widely used in nuclear power plants and nuclear weapons. However, because of the tiny concentrations found in nature,
What's the name of this
uranium
game?
needs to undergo enrichment so that enough uranium-235 is present. Uranium-238 is fissionable by fast neutrons and is fertile.
Well, you can
meaning
leave
it
and
be
rejoin.
transmuted to
And
fissile plutonium-239 in a nuclear reactor.
yeah.
Another fissile isotope, uranium-233, can be produced from natural thorium and is studied for future industrial use in nuclear technology. Uranium-238 has a small probability for spontaneous fission or even induced fission.
My
with
Roblox
fast
is
neutrons.
broken.
Uranium
It's crashing every time I start it.
and to a lesser degree uranium-233 have a much higher fission cross-section for slow neutrons. In sufficient concentration, these isotopes maintain a sustained nuclear chain reaction. This generates the heat in nuclear power reactors and produces the fissile material for nuclear weapons. Depleted uranium-238 is used in kinetic energy penetrators and armor plating. Nate. The 1789 discovery of uranium in the mineral pitchblende is credited to Martin Heinrich Klaproth, who named the new element after the recently discovered planet Uranus. Eugene Melchior Paligid was the first person to isolate the metal, and its radioactive properties were discovered in 1896 by Henri Becquerel. Research by Otto Hahn, Lise Meitner, Enrico Fermi
Dang
and
it.
others, such as J. Robert Oppenheimer starting in 1934 led to its use as a fuel in the nuclear
I gotta
power
download
industry
Roblox
and
too.
in Little Boy, the first nuclear weapon used in war. An ensuing arms race during the Cold War between the United States and the Soviet Union produced tens of thousands of nuclear weapons that used uranium metal and uranium-derived plutonium-239. Dismantling of these weapons and related nuclear facilities is carried out within various nuclear disarmament programs and costs billions of dollars. Weapon-grade uranium obtained from nuclear weapons is diluted with uranium-238 and reused as fuel for nuclear reactors. The development and deployment of these nuclear reactors continue on a global basis as they are powerful sources of CO2-free energy. Spent nuclear fuel forms radioactive waste, which mostly
I just killed it because I'm gonna start it over again. It was not updating.
Please, I want to play for the family.
Okay, I'm getting ready to download Roblox again.
For what?
Well, my Roblox is broken here. I can't play Roblox because every time I start it, it just crashes.
I think, yeah.
Free download. I don't want no dang AVG.
Bowser.
Feather Family. Still has not downloaded.
Because what? Because what?
Because it's stupid. That's why. Oh.
Let's tell download. I think I'm playing something. Click it.
All right, go. If you make, you want me to join?
Yes.
Okay. Well, Roblox, I think it needs to be reinstalled because it's not working. Okay, here we go. Download and install Roblox. Good.
Got your revenge coin.
I'm glad you
Bite it. Okay, click the play button. Okay. Okay, let's hit Kudowojo and we'll hit join. Roblox is now loading. Get ready. Oh, please, dear. I didn't do it. You did it. Okay. Now every time I start it says download and install Roblox. Oh. Oh, hey, Traintastic, what's going on? That's my daughter. Bro, yeah, I guess no, it seems like I don't know. I need to check maybe our hard drive is full or something like that. Cuz she's on Roblox right now. I'm supposed to get on with her. She might get mad at me. But we're down in Georgia, and there's a big nuclear weapons facility in Augusta. It's called the Savannah River Site, and I try to I do environmental work, I guess, or whatever, and it's a real concern the cleanup of these nuclear weapons production facilities. And there's all these people that are involved in nuclear engineering that have expensive degrees, and they want to keep on doing what they're doing because they got to pay their mortgage note. And so they're always going around. Nuclear is great. There's no emissions and all that stuff like that, which is basically a lie. And I like to try to educate people about it. You know, and I was talking about this earlier. Let me see. They say there's no fossil emissions. Okay, when you dig up the uranium out of the ground, you do that with your pinky finger. You know, there's CO2 production at all levels of. So you get uranium, you refine uranium for use in nuclear fuel reactors. What about smelting? All right. Oh, Traintastic. Oh, wow, you yeah, my best friend has and his son also have Asperger's. I hope I don't drive you. I hope I'm not too annoying. But and I've worked with autism students teaching mathematics. All right, take care. See you next time. Thanks for adding me in. Yeah, so you got a uranium metallurgy, right? Like you can type in on Google. I recommend people do this. The nuclear fuel cycle. In fact, I'll do it here. I'll do a demonstration of it. Nuclear fuel cycle. GIF. So you got a nice animated GIF. That's ridiculous. You think you got no fossil emissions with all this, all these trucks and mining equipment I mean, the cement. Like, think of the cement in a nuclear reactor. Like 7%. I mean, do you know what how they make cement? They make it with a big what do you call it? It's a kiln. It's like a rotating kiln. Big heat blast thing. 7% of all carbon emissions are in just making the cement. What about the rebar? Have you ever looked up iron smelting, metallurgy, or whatever? You think there's no fossil emissions in the process of producing all the rebar for a massive nuclear cooling tower or whatever like that? But they'll put it in National Geographic. Oh, you hate the furry animals of the forest if you're against nuclear power because it's clean energy. It's zero emissions. No, it's not zero emissions. That's like a naked lie. All right. What am I gonna do to get Roblox to run? Let me look on. If I was on the technical support desk for Roblox technical support, and the screaming customers were saying, "I pay for my CPU is pegged at 100%, as you can see. Well, no, now it's dropped down to 78. Something was really pegging it. So this is a good kind of scenario. What am I gonna do to get Roblox running? I'm gonna go here and see if it's gonna launch. Installing Roblox, it says. Okay, so to make this a useful stream, right, I want to learn about uranium.
Uranium is a chemical element with symbol and atomic number 92. It is a silvery grey metal in the actinide series of the periodic table. A uranium atom has 92 protons and 92 electrons, of which 6 are valence electrons. Uranium radioactively decays by emitting an alpha particle. The half-life of this decay varies between 159,204.5 billion years for different isotopes, making them useful for dating the age of the Earth. The most common isotopes in natural uranium are uranium-238, which has 146 neutrons and accounts for over 99% of uranium on Earth, and uranium-235, which has 143 neutrons. Uranium has the highest atomic weight of the primordially occurring elements. Its density is about 70% higher than that of lead, and slightly lower than that of gold or tungsten. It occurs naturally in low concentrations of a few parts per million in soil, rock and water, and is commercially extracted from uranium-bearing minerals such as uraninite. 6. Many contemporary uses of uranium exploit its unique nuclear properties. Uranium-235 is the only naturally occurring fissile isotope, which makes it widely used in nuclear power plants and nuclear weapons. However, because of the tiny concentrations found in nature, uranium needs to undergo enrichment so that enough uranium-235 is present. Uranium-238 is fissionable by fast neutrons and is fertile, meaning it can be transmuted to fissile plutonium-239 in a nuclear reactor. Another fissile isotope, uranium-233, can be produced from natural thorium and is studied for future industrial use in nuclear technology. Uranium-238 has a small probability for spontaneous fission or even induced fission with fast neutrons. Uranium-235, and to a lesser degree uranium-233, have a much higher fission cross-section for slow neutrons.
Crash again.
Insufficient concentration. These isotopes maintain
I'm gonna
a
go to
sustained
add and
nuclear
remove
chain
programs. I'm
reaction.
gonna uninstall
This
Roblox and
generates
reinstall
the
it.
heat in nuclear power reactors and produces the fissile material for nuclear weapons. Depleted uranium-238 is used in kinetic energy penetrators and armor plating. 7-8. The 1789 discovery of uranium in the mineral pitchblende is credited to Martin Heinrich Klaproth, who named the new element after the recently discovered planet Uranus. Eugene Melchior Bliggett was the first person to isolate the metal, and its radioactive properties were discovered in 1896 by Henri Becquerel. Research by Otto Hahn, Lise Meitner, Enrico Fermi and others, such as J. Robert Oppenheimer starting in 1934 led to its use as a fuel in the nuclear power industry and in Little Boy, the first nuclear weapon used in war. An ensuing arms race during the Cold War between the United States and the Soviet Union produced tens of thousands of nuclear weapons that used uranium metal and uranium-derived plutonium-239. Dismantling of these weapons and related nuclear facilities is carried out within various nuclear disarmament programs and costs billions of dollars. Weapon-grade uranium obtained from nuclear weapons is diluted with uranium-238 and reused as fuel for nuclear reactors. The development and deployment of these nuclear reactors continue on a global basis. They are powerful sources of CO2-free energy. Spent nuclear fuel forms radioactive waste, which mostly consists of uranium-238 and poses significant health threats and environmental impact. Characteristics. A diagram showing a chain transformation of uranium-235 to uranium-236 to barium-141 and krypton-92. A neutron-induced nuclear fission event involving uranium-235. Uranium is a silvery white, weakly radioactive metal. It is a modest hardness of 6, sufficient to scratch glass and approximately equal to that of titanium, rhodium, manganese and niobium. It is malleable, ductile, slightly paramagnetic, strongly electropositive and a poor electrical conductor. 910, uranium metal has a very high density of 19.1 grams/cm3, 11, denser than lead, 11.3 grams/cm3, 12, but slightly less dense than tungsten and gold, 19.3 grams/cm3, 1314. Uranium metal reacts with almost all non-metal elements, with the exception of the noble gases and their compounds, with reactivity increasing with temperature. 15. Hydrochloric and nitric acids dissolve uranium, but non-oxidizing acids other than hydrochloric acid attack the element very slowly. 9. When finely divided, it can react with cold water. In air, uranium metal becomes coated with a dark layer of uranium oxide. 10. Uranium in ores is extracted chemically and converted into uranium dioxide or other chemical forms usable in industry. Uranium-235 was the first isotope that was found to be fissile. Other naturally occurring isotopes are fissionable, but not fissile. On bombardment with slow neutrons, its uranium-235 isotope will most of the time divide into two smaller nuclei, releasing nuclear binding energy and more neutrons. If too many of these neutrons are absorbed by other uranium-235 nuclei, a nuclear chain reaction occurs that results in a burst of heat or, in special circumstances, an explosion. In a nuclear reactor, such a chain reaction is slowed and controlled by a neutron poison, absorbing some of the free neutrons. Such neutron-absorbent materials are often part of reactor control rods. See nuclear reactor physics for a description of this process of reactor control. As little as 15 pounds, 6.8 kilograms, of uranium-235 can be used to make an atomic bomb. 16. The nuclear weapon detonated over Hiroshima, called Little Boy, relied on uranium fission. However, the first nuclear bomb, the gadget used at Trinity, and the bomb that was detonated over Nagasaki, Pac-Man, were both plutonium bombs. Uranium metal has 3 allotropic forms. 17. Orthorhombic, stable up to 668 degrees Celsius, 1234 degrees Fahrenheit. Orthorhombic, space group number 63, CMCM. Lattice parameters equals 285.4 pm, B equals 587 pm, C equals 495.5 pm. 18. Tetragonal, stable from 668 to 775 degrees Celsius, 1234 to 1427 degrees Fahrenheit. Tetragonal, space group P42/MNM, P42NM, or P4N2, lattice parameters equals 565.6 pm, B equals C equals 1075.9 pm. 18. Body-centered cubic, from 775 degrees Celsius, 1427 degrees Fahrenheit, to melting point. This is the most malleable and ductile state. Body-centered cubic, lattice parameter equals 352.4 pm. 18. Applications. Military. Shiny metallic cylinder with a sharpened tip. The overall length is 9 centimeters and diameter about 2 centimeters. Various militaries use depleted uranium as high-density penetrators. The major application of uranium in the military sector is in high-density penetrators. This ammunition consists of depleted uranium, alloyed with 1 to 2% other elements, such as titanium or molybdenum. 19. At high impact speed, the density, hardness, and pyrophoricity of the projectile enable the destruction of heavily armored targets. Tank armor and other removable vehicle armor can also be hardened with depleted uranium plates. The use of depleted uranium became politically and environmentally contentious after the use of such munitions by the US, UK and other countries during wars in the Persian Gulf and the Balkans raised questions concerning uranium compounds left in the soil. 8. 2021-22, see Gulf War Syndrome. 16. Depleted uranium is also used as a shielding material in some containers used to store and transport radioactive materials. While the metal itself is radioactive, its high density makes it more effective than lead in halting radiation from strong sources such as radium. 9. Other uses of depleted uranium include counterweights for aircraft control surfaces, as ballast for missile re-entry vehicles and as a shielding material. 10. Due to its high density, this material is found in inertial guidance systems and in gyroscopic compasses. 10. Depleted uranium is preferred over similarly dense metals due to its ability to be easily machined and cast as well as its relatively low cost. 23. The main risk of exposure to depleted uranium is chemical poisoning by uranium oxide rather than radioactivity, uranium being only a weak alpha emitter. During the later stages of World War II, the entire Cold War, and to a lesser extent afterwards, uranium-235 has been used as the fissile explosive material to produce nuclear weapons. Initially, 2 major types of fission bombs were built. A relatively simple device that uses uranium-235 and a more complicated mechanism that uses plutonium-239 derived from uranium-238. Later, a much more complicated and far more powerful type of fission, fusion bomb, thermonuclear weapon, was built, that uses a plutonium-based device to cause a mixture of tritium and deuterium to undergo nuclear fusion. Such bombs are jacketed in a non-fissile, unenriched uranium case, and they derive more than half their power from the fission of this material by fast neutrons from the nuclear fusion process. 24. Civilian.
He was
The main
coming
use
so
of
relentless
uranium
on my
in the civilian
behind.
sector is to fuel nuclear power plants. 1
Relentlessly
kilogram of uranium
pursuing me.
235 can theoretically produce about 20 terajoules of energy, 2 times 1013 joules, assuming complete fission, as much energy as 1.5 million kilograms, 1,500 tons of coal. 7. Commercial nuclear power plants use fuel that is typically enriched to around 3% uranium-235. 7. The CANDU and Magnox designs are the only commercial reactors capable of using unenriched uranium fuel. Fuel used for United States Navy reactors is typically highly enriched in uranium-235. The exact values are classified. In a breeder reactor, uranium-238 can also be converted into plutonium through the following reaction. 10. 238 92U plus N239 92U plus minus 239 93 NP minus 239 94 Pu. A glass placed on a glass stand. The plate is glowing green while the stand is colorless. Uranium glass glowing under UV light. Before, and occasionally after, the discovery of radioactivity, uranium was primarily used in small amounts for yellow glass and pottery glazes, such as uranium glass and in festool. 25. The discovery and isolation of radium in uranium ore, pitch blende, by Marie Curie sparked the development of uranium mining to extract the radium, which was used to make glow-in-the-dark paints for clock and aircraft dials. 26-27, this left a prodigious quantity of uranium as a waste product, since it takes 3 tons of uranium to extract 1 gram of radium. This waste product was diverted to the glazing industry, making uranium glazes very inexpensive and abundant. Besides the pottery glazes, uranium tile glazes accounted for the bulk of the use, including common bathroom and kitchen tiles which can be produced in green, yellow, mauve, black, blue, red and other colors. The uranium glaze on a sensor saw ceramic glowing under UV light. A glass cylinder capped on both ends with metal electrodes. Inside the glass bulb there is a metal cylinder connected to the electrodes. Uranium glass uses lead-in seals in a vacuum capacitor. Uranium was also used in photographic chemicals, especially uranium nitrate as a toner. 10. In lamp filaments for stage lighting bulbs. 28. To improve the appearance of dentures. 29. And in the leather and wood industries for stains and dyes. Uranium salts are mordants of silk or wool. Uranyl acetate and uranyl formate are used as electron-dense stains in transmission electron microscopy to increase the contrast of biological specimens in ultraviolet sections and in negative staining of viruses, isolated cell organelles and macromolecules. The discovery of the radioactivity of uranium ushered in additional scientific and practical uses of the element. The long half-life of the isotope uranium-238, 4.47 times 109 years, makes it well suited for use in estimating the age of the earliest igneous rocks and for other types of radiometric dating, including uranium-thorium dating, uranium-lead dating and uranium-uranium dating. Uranium metal is used for X-ray targets in the making of high-energy X-rays. 10. History. Pre-discovery use. The use of uranium in its natural oxide form dates back to at least the year 79, when it was used in the Roman Empire to add a yellow color to ceramic glazes. 10. Yellow glass with 1% uranium oxide was found in a Roman villa on Cape Posillipo in the Bay of Naples, Italy, by R.T. Gunter of the University of Oxford in 1912. 30. Starting in the late Middle Ages, pitchblende was extracted from the Habsburg silver mines in Joachimsthal, Bohemia, now Jakimov in the Czech Republic, and was used as a coloring agent in the local glass-making industry. 31. In the early 19th century, the world's only known sources of uranium ore were these mines. Mining for uranium in the ore mountains ceased on the German side after the Cold War ended and Stag-Wismut was wound down. On the Czech side, there were attempts during the uranium price bubble of 2007 to restart mining, but those were quickly abandoned following a fall in uranium prices. 30 to 33. Discovery. The planet Uranus, which uranium is named after. The discovery of the element is credited to the German chemist Martin Heinrich Klaproth. While he was working in his experimental laboratory in Berlin in 1789, Klaproth was able to precipitate a yellow compound, likely sodium duranate, by dissolving pitchblende in nitric acid and neutralizing the solution with sodium hydroxide. 31. Klaproth assumed the yellow substance was the oxide of a yet undiscovered element and heated it with charcoal to obtain a black powder, which he thought was the newly discovered metal itself. In fact, that powder was an oxide of uranium. 31-34. He named the newly discovered element after the planet Uranus, named after the primordial Greek god of the sky, which had been discovered 8 years earlier by William Herschel. 35. In 1841, Eugene Melchior Pliget, professor of analytical chemistry at the Conservatoire National des Arts et Métiers, Central School of Arts and Manufactures, in Paris, isolated the first sample of uranium metal by heating uranium tetrachloride with potassium. 31-36. Two fuzzy black features on a fuzzy white paper-like background. There is a handwriting at the top of the picture. Antoine-Henri Becquerel discovered the phenomenon of radioactivity by exposing a photographic plate to uranium in 1896. Henri Becquerel discovered radioactivity by using uranium in 1896. 15. Becquerel made the discovery in Paris by leaving a sample of a uranium salt, K2UO2 SO42, potassium uranyl sulfate, on top of an unexposed photographic plate in a drawer, noting that the plate had become fogged. 37. He determined that a form of invisible light or rays emitted by uranium had exposed the plate. During World War I, when the Central Powers suffered a shortage of molybdenum to make artillery gun barrels and high-speed tool steels, they routinely substituted ferruranium alloys, which present many of the same physical characteristics. When this practice became known in 1916, the USA government requested several prominent universities to research these uses for uranium, and tools made with these formulas remained in use for several decades. 38-39. Ending when Manhattan Project and the Cold War placed a large demand on uranium for research and weapon development. Fission research. Cubes and cuboids of uranium produced during the Manhattan Project. A team led by Enrico Fermi in 1934 observed that bombarding uranium with neutrons produces the emission of beta rays, electrons or positrons from the elements produced. See beta particle. 40. The fission products were at first mistaken for new elements with atomic numbers 93 and 94, which the Dean of the Faculty of Rome, Orso Mario Corbino, christened arsonium and hesperium, respectively. 41, 42, 43, 44. The experiments leading to the discovery of uranium's ability to fission, break apart into lighter elements and release binding energy were conducted by Otto Hahn and Fritz Strassmann. 40. In Hahn's laboratory in Berlin, Lise Meitner and her nephew, the physicist Otto Robert Friis, published the physical explanation in February 1939 and named the process nuclear fission. 45. Soon after, Fermi hypothesized that the fission of uranium might release enough neutrons to sustain a fission reaction. Confirmation of this hypothesis came in 1939, and later work found that on average about 2.5 neutrons are released by each fission of the rare uranium isotope uranium-235. 40. Fermi urged Alfredo Zenia to separate uranium isotopes for determination of the fissile component, and on the 29th of February 1940, Zenia used an instrument he built at the University of Minnesota to separate the world's first uranium-235 sample in the Tate Laboratory. After mail to Columbia University's cyclotron, John Dunning confirmed the sample to be the isolated fissile material on the 1st of March. 46. Further work found that the far more common uranium-238 isotope can be transmuted into plutonium, which, like uranium-235, is also fissile by thermal neutrons. These discoveries led numerous countries to begin working on the development of nuclear weapons and nuclear power. Despite fission having been discovered in Germany, the Uranverein, Uranium Club, Germany's wartime project to research nuclear power and/or weapons was hampered by limited resources, infighting, the exile or non-involvement of several prominent scientists in the field, and several crucial mistakes such as failing to account for impurities in available graphite samples, which made it appear less suitable as a neutron moderator than it is in reality. Germany's attempts to build a natural uranium heavy water reactor had not come close to reaching criticality by the time the Americans reached Hagelosh, the site of the last German wartime reactor experiment. 47. On the 2nd of December 1942, as part of the Manhattan Project, another team led by Enrico Fermi was able to initiate the first artificial self-sustained nuclear chain reaction, Chicago Bile 1. An initial plan using enriched uranium-235 was abandoned as it was as yet unavailable in sufficient quantities. 48. Working in a lab below the stands of Stagg Field at the University of Chicago, the team created the conditions needed for such a reaction by piling together 360 tons of graphite, 53 tons of uranium oxide, and 5.5 tons of uranium metal, a majority of which was supplied by Westinghouse lamp plant in a makeshift production process. 40-49. Nuclear weaponry. White fragmented mushroom-like smoke cloud evolving from the ground. The mushroom cloud over Hiroshima after the dropping of the uranium-based atomic bomb nicknamed Little Boy. Two major types of atomic bombs were developed by the United States during World War II, a uranium-based device, codenamed Little Boy, whose fissile material was highly enriched uranium, and a plutonium-based device, see Trinity Test, and Fat Man, whose plutonium was derived from uranium-238. The uranium-based Little Boy device became the first nuclear weapon used in war when it was detonated over the Japanese city of Hiroshima on the 6th of August 1945, exploding with a yield equivalent to 12,500 tons of trinitrotoluene. The blast and thermal wave of the bomb destroyed nearly 50,000 buildings and killed approximately 75,000 people. See atomic bombings of Hiroshima and Nagasaki. 37. Initially it was believed that uranium was relatively rare, and that nuclear proliferation could be avoided by simply buying up all known uranium stocks, but within a decade large deposits of it were discovered in many places around the world. 50-51. Reactors. An industrial room with 4 large illuminated light bulbs hanging down from a bar. 4 light bulbs lit with electricity generated from the first artificial electricity producing nuclear reactor, EBRI, 1951. The X-10 graphite reactor at Oak Ridge National Laboratory, ORNL, in Oak Ridge, Tennessee, formerly known as the Clinton Pile and X-10 Pile, was the world's second artificial nuclear reactor, after Enrico Fermi's Chicago Pile, and was the first reactor designed and built for continuous operation. Argonne National Laboratory's experimental breeder reactor I, located at the Atomic Energy Commission's National Reactor Testing Station near Akko, Idaho, became the first nuclear reactor to create electricity on the 20th of December 1951. 52. Initially, 4 150-watt light bulbs were lit by the reactor, but improvements eventually enabled it to power the whole facility. Later, the town of Arco became the first in the world to have all its electricity come from nuclear power generated by Borax 3, another reactor designed and operated by Argonne National Laboratory. 53-54, the world's first commercial-scale nuclear power station, Obninsk in the Soviet Union, began generation with its reactor AM-1 on the 27th of June 1954. Other early nuclear power plants were Calder Hall in England, which began generation on the 17th of October 1956, 55, and the Shippingport Atomic Power Station in Pennsylvania, which began on the 26th of May 1958. Nuclear power was used for the first time for propulsion by a submarine, the USS Nautilus, in 1954. 40-56. Prehistoric naturally occurring fission. Main article, Natural Nuclear Fission Reactor. In 1972, the French physicist Francis Perrin discovered 15 ancient and no longer active natural nuclear fission reactors in 3 separate ore deposits at the Eklo mine in Gabon, West Africa, collectively known as the Eklo fossil reactors. The ore deposit is 1.7 billion years old.
Got enough?
Uranium-235 constituted about 3% of the total uranium on Earth. 57. This is high enough to permit a sustained nuclear fission chain reaction to occur, provided other supporting conditions exist. The capacity of the surrounding sediment to contain the health-threatening nuclear waste products has been cited by the US federal government as supporting evidence for the feasibility to store spent nuclear fuel at the Yucca Mountain Nuclear Waste Repository. 57. Contamination and the Cold War legacy. A graph showing evolution of number of nuclear weapons in the US and USSR and in the period 1945 to 2005. US dominates early and USSR later years with a crossover around 1978. US and USSR/Russian nuclear weapons stockpiles, 1945 to 2005. Above-ground nuclear tests by the Soviet Union and the United States in the 1950s and early 1960s and by France into the 1970s and 1980s. 23. Spread a significant amount of fallout from uranium daughter isotopes around the world. 58. Additional fallout and pollution occurred from several nuclear accidents. 59. Uranium miners have a higher incidence of cancer. An excess risk of lung cancer among Navajo uranium miners, for example, has been documented and linked to their occupation. 60. The Radiation Exposure Compensation Act, a 1990 law in the US, required $100,000 in compassion payments to uranium miners diagnosed with cancer or other respiratory ailments. 61. During the Cold War between the Soviet Union and the United States, huge stockpiles of uranium were amassed and tens of thousands of nuclear weapons were created using enriched uranium and plutonium made from uranium. After the breakup of the Soviet Union in 1991, an estimated 600 short tons, 540 metric tons, of highly enriched weapons-grade uranium, enough to make 40,000 nuclear warheads, had been stored in often inadequately guarded facilities in the Russian Federation and several other former Soviet states. 16. Police in Asia, Europe, and South America on at least 16 occasions from 1993
What kind of feathers?
to 2005 have intercepted
I guess
shipments of
so.
smuggled bomb-grade
I would have to
uranium
look
or
that up in the
plutonium,
Encyclopedia
most of which was
Wikipedia.
from ex-Soviet sources. 16.
To make sure I was
From
right.
1993 to 2005, the Material Protection, Control, and Accounting Program, operated by the federal government of the United States, spent approximately US $550 million to help safeguard uranium and plutonium stockpiles in Russia. This money was used for improvements and security enhancements at research and storage facilities. 16. Safety of nuclear facilities in Russia has been significantly improved since the stabilization of political and economical turmoil of the early 1990s. For example, example, in 1993 there were 29 incidents, ranking above level 1 on the International Nuclear Event Scale, and this number dropped under 4 per year in 1995 to 2003. The number of employers
welcome.
receiving annual radiation doses above 20
Hug.
millisieverts, which is equivalent
Yeah,
to a
very
single
happy.
full-body CT scan, 62, saw a strong decline around 2000. In November 2015, the Russian government approved a federal program for nuclear and radiation safety for 2016 to 2030 with a budget of 562 billion rubles, $8 billion. Its key issue is the deferred liabilities accumulated during the 70 years of the nuclear industry, particularly during the time of the Soviet Union. Approximately 73% of the budget will be spent on decommissioning aged and obsolete nuclear reactors and nuclear facilities, especially those involved in state defense programs. 20% will go in processing and disposal of nuclear fuel and radioactive waste, and 5% into monitoring and ensuring of nuclear and radiation safety. 63. Occurrence. Origin. Along with all elements having atomic weights higher than that of iron, uranium is only naturally formed by the R process, rapid neutron capture, in
You're my best
supernovae and neutron
pal.
star mergers. 64. Primordial thorium and uranium are
You wanna
only
take a
produced
nap?
in the R process, because the S process, slow
Well,
neutron
Roblox is
capture,
broken on my
is too
computer right
slow
now. I'm
and
trying to
cannot
fix it,
pass the
but
gap of
so far it hasn't
instability
worked.
after bismuth.
So as soon as I copy this
65,
file again, I'll
66.
try to
Besides the two extant primordial uranium isotopes,
call someone.
235U and 238U, the R process also
Hello, this
produced
is
significant
Roblox
quantities of
user
236U,
1,074,000,074.
which has a shorter half-life and so is an extinct radionuclide, having long since decayed completely to 232 Th. Uranium-236 was itself enriched by the decay of 244 Pu, accounting for the observed higher than expected abundance of thorium and lower than expected abundance of uranium. 67. While the natural abundance of uranium has been supplemented by the decay of extinct 242 Pu, half-life 0.375 million years, and 247 cm, half-life 16 million years, producing 238U and 235U respectively. This occurred to an almost negligible extent due to the shorter half-lives of these parents and their lower production than 236U and 244 Pu, the parents of thorium. The 247 cm:235U ratio at the formation of the solar system was 7.0 plus minus 1.6 times 10 minus 5. 68. Biotic and abiotic. Main article, uranium in the environment. A shiny grey 5 cm piece of matter with a rough surface. Uraninite, also known as pitchblende, is the most common ore mine to extract uranium. The evolution of Earth's radiogenic heat flow over time, contribution from 235U in red and from 238U in green. Uranium is a naturally occurring element that can be found in low levels within all rock, soil, and water. Uranium is the 51st element in order of abundance in the Earth's crust. Uranium is also the highest numbered element to be found naturally in significant quantities on Earth, and is almost always found combined with other elements. 10. The decay of uranium, thorium, and potassium-40 in the Earth's mantle is thought to be the main source of heat. 6970 that keeps the Earth's
I'm trying to see if
core in
it's
a
gonna
liquid
work.
state and drives mantle convection, which in turn drives plate tectonics. Uranium's average concentration in the Earth's crust is, depending on the reference, 2 to 4 parts per million, 923, or about 40 times as abundant as silver. 15. The Earth's crust from the surface to 25 kilometers, 15 miles, down is calculated to contain 1,017 kilograms, 2 times 1,017 pounds, of uranium, while the oceans may contain 1,013 kilograms, 2 times 1,013 pounds. 9. The concentration of uranium in soil ranges from 0.7 to 11 parts per million, up to 15 parts per million in farmland soil due to use of phosphate fertilizers, 71, and its concentration in seawater is 3 parts per billion, 23. Uranium is more plentiful than antimony, tin, cadmium, mercury, or silver, and it is about as abundant as arsenic or molybdenum. 1023. Uranium is found in hundreds of minerals, including uraninite, the most common uranium ore, carnotite, autunite, uraninite, taurbanite,
Ellie went to sleep. She just
10.
went to sleep.
Significant concentrations of uranium occur in some substances such as phosphate rock deposits, and minerals such as lignite and monazite sands in uranium-rich ores. 10. It is recovered commercially from sources with as little as 0.1% uranium. 15. Some bacteria, such as Shigella putrefaciens, Jabactomets lyridicens and some strains of Burkholderia fungorum, use uranium for their growth and convert UV to U4. 72-73, recent research suggests that this pathway includes reduction of the soluble UV via an intermediate UV pentavalent state. 74-75, other organisms, such as the lichen Drapelia involuta, or microorganisms such as the bacterium Citrobacter, can absorb concentrations of uranium that are up to 300 times the level of their environment. 76. Citrobacter species absorb uranyl ions when given glycerol phosphate or other similar organic phosphates. After 1 day, 1 gram of bacteria can encrust themselves with 9 grams
You can always
of
draw
uranyl
something, just
phosphate
ask Daddy.
crystals. This creates
Let me
the possibility that these
hold Ellie
organisms
for a
could
second.
be
I'll get
used
you
in
your
bioremediation
notebook.
to contaminate uranium-polluted water. 3177. The proteobacterium Jobacter has also been shown to bioremediate uranium in groundwater. 78. The mycorrhizal fungus Glomus intraradices increases uranium content in the roots of its symbiotic plant. 79. In nature, uranium Vi forms highly soluble carbon-8 complexes at alkaline pH. This leads to an increase in mobility and availability of uranium to groundwater and soil from nuclear wastes, which leads to health hazards. However, it is difficult to precipitate uranium as phosphate in the presence of excess carbonate at alkaline pH. Asphingomonas sp. Strain BZA1 has been found to express a high-activity alkaline phosphatase, PHOC, that has been applied for bioprecipitation of uranium as uranyl phosphate species from alkaline solutions. The precipitation ability was enhanced by overexpressing PHOC protein in E. coli. 80. Plants absorb some uranium from soil. Dry weight concentrations of uranium in plants range from 5 to 60 parts per billion, and ash from burnt wood can have concentrations up to 4 parts per million. 31. Dry weight concentrations of uranium in food plants are typically lower, with 1 to 2 micrograms per day ingested through the food people eat. 31. Production and mining. Main article, uranium mining. Worldwide production of uranium in 2021 amounted to 48,332 tons, of which 21,819 tons, 45%, was mined in Kazakhstan. Other important uranium mining countries are Namibia, 5,753 tons, Canada, 4,693 tons, Australia, 4,192 tons, Uzbekistan, 3,500 tons, and Russia, 2,635 tons. 81. Uranium ore is mined in several ways, by open pit, underground, in situ leaching, and borehole mining. See uranium mining. 7. Low-grade uranium ore mine typically contains 0.01 to 0.25% uranium oxides. Extensive measures must be employed to extract the metal from its ore. 82. High-grade ores found in Athabasca Basin deposits in Saskatchewan, Canada can contain up to 23% uranium oxides on average. 83. Uranium ore is crushed and rendered into a fine powder and then leached with either an acid or alkali. The leachate is subjected to one of several sequences of precipitation, solvent extraction, and ion exchange. The resulting mixture, called yellow cake, contains at least 75% uranium oxides U3O8. Yellow cake is then calcined to remove impurities from the milling process before refining and conversion. 84. Commercial grade uranium can be produced through the reduction of uranium halides with alkali or alkaline earth metals. 10. Uranium metal can also be prepared through electrolysis of CuF. 5 or UF. 4. Dissolved in molten calcium chloride, CaCl. 2. And sodium chloride, NaCl, solution. 10. Very pure uranium is produced through the thermal decomposition of uranium halides on a hot filament. 10. World uranium production, mines, and demand 81. World uranium production, mines, and demand 81. A yellow sand-like rhombic mass on black background. Yellow cake is a concentrated mixture of uranium oxides that is further refined to extract pure uranium. Uranium production 2015, in tons 85. Uranium production 2015, in tons 85. Resources and reserves. Uranium price 1990 to 2022. It is estimated that 6.1 million tons of uranium exists in ore reserves that are economically viable at $130 per kg of uranium, 86, while 35 million tons are classed as mineral resources, reasonable prospects for eventual economic extraction. 87. Australia has 28% of the world's known uranium ore reserves, 86. And the world's largest single uranium deposit is located at the Olympic Dam mine in South Australia. 88. There is a significant reserve of uranium in Bakema, a sub-prefecture in the prefecture of Mbomo in the Central African Republic. 89. Some uranium also originates from dismantled nuclear weapons. 90. For example, in 1993 to 2013, Russia supplied the United States with 15,000 tons of low-enriched uranium within the megatons to megawatts program. 91. An additional 4.6 billion tons of uranium are estimated to be dissolved in seawater. Japanese scientists in the 1980s showed that extraction of uranium from seawater using ion exchanges was technically feasible. 92-93. There have been experiments to extract uranium from seawater, 94, but the yield has been low due to the carbonate present in the water. In 2012, ORNL researchers announced the successful development of a new absorbent material dubbed HiCap, which performs surface retention of solid or gas molecules, atoms or ions, and also effectively removes toxic metals from water, according to results verified by researchers at Pacific Northwest National Laboratory. 95-96. Supplies. Main article, uranium market. See also, 2000s commodities boom. Monthly uranium spot price in US dollar per pound. The 2007 price peak is clearly visible. 97. In 2005, 10 countries accounted for the majority of the world's concentrated uranium oxides: Canada, 27.9%, Australia, 22.8%, Kazakhstan, 10.5%, Russia, 8.0%, Namibia, 7.5%, Niger, 7.4%, Uzbekistan, 5.5%, the United States, 2.5%, Argentina, 2.1%, and Ukraine, 1.9%. 98. In 2008, Kazakhstan was forecast to increase production and become the world's largest supplier of uranium by 2009. 99-100, the prediction came true, and Kazakhstan does dominate the world's uranium market since 2010. In 2021, its share was 45.1%, followed by Namibia, 11.9%, Canada, 9.7%, Australia, 8.7%, Uzbekistan, 7.2%, Niger, 4.7%, Russia 5.5%, China 3.9%, India 1.3%, Ukraine 0.9%, and South Africa 0.8%, with a world total production of 48,332 tons. 81. Most of uranium was produced not by conventional underground mining of ores, 29% of production, but by in situ leaching, 66%. 81. 101. In the late 1960s, UN geologists also discovered major uranium deposits and other rare mineral reserves in Somalia. The find was the largest of its kind, with industry experts estimating the deposits at over 25% of the world's then-known uranium reserves of 800,000 tons. 102. The ultimate available supply is believed to be sufficient for at least the next 85 years. 87. Although some studies indicate underinvestment in the late 20th century may produce supply problems in the 21st century. 103. Uranium deposits seem to be log normal distributed. There is a 300-fold increase in the amount of uranium recoverable for each 10-fold decrease in ore grade. 104. In other words, there is little high-grade ore and proportionately much more low-grade ore available. Compounds. Reactions of uranium metal. Oxidation states and oxides. Oxides. Ball and stick model of layered crystal structure containing two types of atoms. Ball and stick model of cubic-like crystal structure containing two types of atoms. Triranium octoxide, left, and uranium dioxide, right, are the two most common uranium oxides. Calcined uranium yellowcake, as produced in many large mills, contains a distribution of uranium oxidation species in various forms ranging from most oxidized to least oxidized. Particles with short residence times in a calciner will generally be less oxidized than those with long retention times or particles recovered in the stack's scrubber. Uranium content is usually referenced here. 308, which dates to the days of the Manhattan Project when U-308 was used as an analytical chemistry reporting standard. 105. Phase relationships in the uranium-oxygen system are complex. The most important oxidation states of uranium are uranium-4 and uranium-Vi, and their two corresponding oxides are, respectively, uranium dioxide, UO2, and uranium trioxide, UO3. 106. Other uranium oxides such as uranium monoxide, uranium pentoxide, U2O5, and uranium peroxide, UO4-2H2O, also exist. The most common forms of uranium oxide are triranium octoxide, U3O8, and UO2. 107. Both oxide forms are solids that have low solubility in water and are relatively stable over a wide range of environmental conditions. Triranium octoxide is, depending on conditions, the most stable compound of uranium and is the form most commonly found in nature. Uranium dioxide is the form in which uranium is most commonly used as a nuclear reactor fuel. 107. At ambient temperatures, UO2 will gradually convert to U3O8. Because of their stability, uranium oxides are generally considered the preferred chemical form for storage or disposal. 107. Aqueous chemistry. Uranium in its oxidation states 3, 4, 5, 6. Salts of many oxidation states of uranium are water-soluble and may be studied in aqueous solutions. The most common ionic forms are U3+, brown-red, U4+, green, UO+, 2, unstable, and UO2+, 2, yellow, for U3, U4, UV, and UVi, respectively. 108. A few solid and semi-metallic compounds such as UO and US exist for the formal oxidation state uranium-2, but no simple ions are known to exist in solution for that state. Ions of U3+, liberate hydrogen from water and are therefore considered to be highly unstable. The UO2 plus 2 ion represents the uranium Vi state and is known to form compounds such as uranyl carbonate, uranyl chloride and uranyl sulfate. UO2 plus 2 also forms complexes with various organic chelating agents, the most commonly encountered of which is uranyl acetate. 108. Unlike the uranyl salts of uranium and polyatomic ion uranium oxide cationic forms, the uranates, salts containing a polyatomic uranium oxide anion, are generally not water-soluble. Carbonates. The interactions of carbonate anions with uranium Vi cause the Pauwels diagram to change greatly when the medium is changed from water to a carbonate-containing solution. While the vast majority of carbonates are insoluble in water, students are often taught that all carbonates other than those of alkali metals are insoluble in water. Uranium carbonates are often soluble in water. This is because a UVi cation is able to bind 2 terminal oxides and 3 or more carbonates to form anionic complexes. Pauwels diagrams 109. A graph of potential versus pH showing stability regions of various uranium compounds. A graph of potential versus pH showing stability regions of various uranium compounds. Uranium in a non-complexing aqueous medium, for example perchloric acid, sodium hydroxide. 109. Uranium in carbonate solution. A graph of potential versus pH showing stability regions of various uranium compounds. A graph of potential versus pH showing stability regions of various uranium compounds. Relative concentrations of the different chemical forms of uranium in a non-complexing aqueous medium, for example perchloric acid, sodium hydroxide. 109. Relative concentrations of the different chemical forms of uranium in an aqueous carbonate solution. 109. Effects of pH. The uranium fraction diagrams in the presence of carbonate illustrate this further. When the pH of a uranium Vi solution increases, the uranium is converted to a hydrated uranium oxide hydroxide, and at high pHs it becomes an anionic hydroxide complex. When carbonate is added, uranium is converted to a series of carbonate complexes if the pH is increased. One effect of these reactions is increased solubility of uranium in the pH range 6 to 8, a fact that has a direct bearing on the long-term stability of spent uranium dioxide nuclear fuels. Hydrides, carbides and nitrides. Uranium metal heated to 250 to 300 degrees Celsius, 482 to 572 degrees Fahrenheit, reacts with hydrogen to form uranium hydride. Even higher temperatures will reversibly remove the hydrogen. This property makes uranium hydrides convenient starting materials to create reactive uranium powder along with various uranium carbide, nitride, and halide compounds. 110. 2 crystal modifications of uranium hydride exist, and form that is obtained at low temperatures and a form that is created when the formation temperature is above 250 degrees Celsius. 110. Uranium carbides and uranium nitrides are both relatively inert semimetallic compounds that are minimally soluble in acids, react with water, and can ignite in air to form U. 308. 110. Carbides of uranium include uranium monocarbide, UC, uranium dicarbide, UC, 2, and uranium tricarbide, U2C. 3. Both UC and UC2 are formed by adding carbon to molten uranium or by exposing the metal to carbon monoxide at high temperatures. Stable below 1800 degrees Celsius, U2C. 3 is prepared by subjecting a heated mixture of UC and UC2 to mechanical stress. 111. Uranium nitrides obtained by direct exposure of the metal to nitrogen include uranium mononitride, UN, uranium dinitride, UN2, and uranium trinitride, U2 newtons. 3. 111. Halides. snow-like substance in a sealed glass ampoule. Uranium hexafluoride is the feedstock used to separate uranium-235 from natural uranium. All uranium fluorides are created using uranium tetrafluoride, UF4, UF4 itself is prepared by hydrofluorination of uranium dioxide. 110, reduction of UF4 with hydrogen at 1000 degrees Celsius produces uranium trifluoride, UF3. Under the right conditions of temperature and pressure, the reaction of solid UF4 with gaseous uranium hexafluoride, UF6, can form the intermediate fluorides of U2F, 9, U4F, 17, and U5, 110. At room temperatures, U6 has a high vapor pressure, making it useful in the gaseous diffusion process to separate the rare uranium-235 from the common uranium-238 isotope. This compound can be prepared from uranium dioxide and uranium hydride by the following process. 110. UO2 plus 4HF 4 plus 2H 2O 500 degrees Celsius endothermic UF 4 plus F 2 UF 6 350 degrees Celsius endothermic. The resulting UF6, a white solid, is highly reactive. By fluorination, easily sublimes, emitting a vapor that behaves as a nearly ideal gas, and is the most volatile compound of uranium known to exist. 110. One method of preparing uranium tetrachloride, Ag4, is to directly combine chlorine with either uranium metal or uranium hydride. The reduction of Ag4 by hydrogen produces uranium trichloride, Ag3, while the higher chlorides of uranium are prepared by reaction with additional chlorine. 110. All uranium chlorides react with water and air. Bromides and iodides of uranium are formed by direct reaction of, respectively, bromine and iodine with uranium or by adding A3 to those elements' acids. 110. Known examples include UB3, UB4, UI3, and UI4. UI5 has never been prepared. Uranium oxyhalides are water soluble and include UO2F, 2 UOC, 2 UO, 2Cl, 2, and UO2Br, 2. Stability of the oxyhalides decreases, the atomic weight of the component halide increases. 110. Isotopes. Main article, Isotopes of uranium. Uranium, like all elements with an atomic number greater than 82, has no stable isotopes. All isotopes of uranium are radioactive because the strong nuclear force does not prevail over electromagnetic repulsion in nuclides containing more than 82 protons. 112. Nevertheless, the two most stable isotopes, uranium-238 and uranium-235, have half-lives long enough to occur in nature as primordial radionuclides, with measurable quantities having survived since the formation of the Earth. 113. These two nuclides, along with thorium-232, are the only confirmed primordial nuclides heavier than nearly stable bismuth-209. 114. Natural uranium consists of three major isotopes: uranium-238, 99.28% natural abundance, uranium-235, 0.71%, and uranium-234, 0.0054%. There are also four other trace isotopes: uranium-239, which is formed when 238U undergoes spontaneous fission, releasing neutrons that are captured by another 238U atom, uranium-237, which is formed when 238U captures a neutron but emits two more, which then decays to neptunium-237, uranium-236, which occurs in trace quantities due to neutron capture on 235U and as a decay product of plutonium-244, 114, and finally, uranium-233, which is formed in the decay chain of neptunium-237. Uranium-238 is the most stable isotope of uranium, with a half-life of about 4.463 times 109 years, 4, roughly the age of the Earth. Uranium-238 is predominantly an alpha emitter, decaying to thorium-234. It ultimately decays through the uranium series, which has 18 members, into lead-206. 15. Uranium-238 is not fissile, but is a fertile isotope, because after neutron activation it can be converted to plutonium-239, another fissile isotope. Indeed, the 238U nucleus can absorb one neutron to produce the radioactive isotope uranium-239. 239U decays by beta emission to neptunium-239, also a beta emitter, that decays in its turn, within a few days into plutonium-239. 239Pu was used as fissile material in the first atomic bomb detonated in the Trinity test on the 15th of July 1945 in New Mexico. 40. Uranium-235 has a half-life of about 7.04 times 108 years. It is the next most stable uranium isotope after 238U and is also predominantly an alpha emitter, decaying to thorium-231. 4. Uranium-235 is important for both nuclear reactors and nuclear weapons, because it is the only uranium
She's
isotope
cutting up
existing in
a sheet
nature
of
on
my
Earth in any significant
notes.
amount
Right,
that is
I did
fissile. This means that it can be split into 2 or 3
the
fragments,
derivation of the
fission
product
products,
rule for
by thermal
calculus,
neutrons.
for taking
15.
derivatives
The decay
of the
chain of
products of functions.
235U, which is called the actinium series,
It's okay.
has 15 members and eventually decays into lead-207. 15. The constant rates of decay in these decay series makes the comparison of the ratios of parent to daughter elements useful in radiometric dating. Uranium-236 has a half-life of 2.342 times 107 years, 4.
That should
and
be
is not
times 10
found
to
in
the
significant
7th.
quantities in nature. The half-life of
10
uranium-236
million.
is too short for it to be primordial, though it has been identified as an extinct progenitor of its alpha decay daughter, thorium-232. 67. Uranium-236 occurs in spent nuclear fuel when neutron capture on 235U does not induce fission, or as a decay product of plutonium-240. Uranium-236 is not fertile, as 3 more neutron captures are required to produce fissile 239Pu, and is not itself fissile. As such, it is considered long-lived radioactive waste. 117. Uranium-234 is a member of the uranium series and occurs in equilibrium with its progenitor, 238U. It undergoes alpha decay with a half-life of 245,500 years, 4, and decays to lead-206 through a series of relatively short-lived isotopes. Uranium-233 undergoes alpha decay with a half-life of 160,000 years and, like 235U, is fissile. 10. It can be bred from thorium-232 via neutron bombardment, usually in a nuclear reactor. This process is known as the thorium fuel cycle. Owing to the fissility of 233U and the greater natural abundance of thorium, 3 times that of uranium, 118, 233U has been investigated for use as nuclear fuel as a possible alternative to 235U and 239Pu. 119. though is not in widespread use as of 2022. 118. The decay chain of uranium-233 forms part of the Neptunium series and ends at nearly stable bismuth-209, half-life 2.01 times 1019 years 4, and stable
That should be
thallium-205.
10 to the 19th power.
Uranium-232 is an alpha emitter with a half-life of 68.9 years. 4. This isotope is produced as a byproduct in production of 233U and is considered a nuisance, as it is not fissile and decays through short-lived alpha and gamma emitters such as 208Tl. 119. It is also expected that thorium-232 should be able to undergo double beta decay, which would produce uranium-232, but this has not yet been observed experimentally. 4. All isotopes from 232U to 236U inclusive of minor cluster decay branches, less than 10-10%, and all these bar 233U, in addition to 238U, of minor spontaneous fission branches. 4. The greatest branching ratio for spontaneous fission is about 5 times 10⁻⁵% for 238U, or about 1 in every 2 million decays. 120. The shorter-lived trace isotopes 237U and 239U exclusively undergo beta decay, with respective half-lives of 6.752 days and 23.45 minutes. 4. In total, 28 isotopes of uranium have been identified, ranging in mass number from 214-121 to 242, with the exception of 220. For 122, among the uranium isotopes not found in natural samples or nuclear fuel, the longest lived is 230U, an alpha emitter with a half-life of 20.23 days. 4. This isotope has been considered for use in targeted alpha particle therapy. Dat. 123. All other isotopes have half-lives shorter than 1 hour, except for 231U, half-life 4.2 days, and 240U, half-life 14.1 hours. 4. The shortest-lived known isotope is 221U, with a half-life of 660 nanoseconds, and it is expected that the hitherto unknown 220U has an even shorter half-life. 124. The proton-rich isotopes lighter than 232U primarily undergo alpha decay, except for 229U and 231U, which decay to protactinium isotopes via positron emission and electron capture, respectively. The neutron-rich 240U and 242U undergo beta decay to form neptunium isotopes. 4. Enrichment. Main article, Enriched Uranium. A photo of a large hall filled with arrays of long white standing cylinders. Cascades of gas centrifuges are used to enrich uranium or to concentrate its fissionable isotopes. In nature, uranium is found as uranium-238, 99.2742%, and uranium-235, 0.7204%. Isotope separation concentrates enriches the fissile uranium-235 for nuclear weapons and most nuclear power plants, except for gas-cooled reactors and pressurized heavy water reactors. Most neutrons released by a fissioning atom of uranium-235 must impact other uranium-235 atoms to sustain the nuclear chain reaction. The concentration and amount of uranium-235 needed to achieve this is called a critical mass. To be considered enriched, the uranium-235 fraction should be between 3% and 5%. 125. This process produces huge quantities of uranium that is depleted of uranium-235 and with a correspondingly increased fraction of uranium-238, called depleted uranium or DU. To be considered depleted, the uranium-235 isotope concentration should be no more than 0.3%. 126. The price of uranium has risen since 2001, so enrichment tailings containing more than 0.35% uranium-235 are being considered for re-enrichment, driving the price of depleted uranium hexafluoride above $130 per kilogram in July 2007 from $5 in 2001. 126. The gas centrifuge process, where gaseous uranium hexafluoride, U6, is separated by the difference in molecular weight between 235 U6 and 238 U6 using high-speed centrifuges, is the cheapest and leading enrichment process. 37. The gaseous diffusion process had been the leading method for enrichment and was used in the Manhattan Project. In this process, uranium hexafluoride is repeatedly diffused through a silver-zinc membrane, and the different isotopes of uranium are separated by diffusion rate. Since uranium-238 is heavier, it diffuses slightly slower than uranium-235. 37. The molecular laser isotope separation method employs a laser beam of precise energy to sever the bond between uranium-235 and fluorine. This leaves uranium-238 bonded to fluorine and allows uranium-235 metal to precipitate from the solution. 7. An alternative laser method of enrichment is known as atomic vapor laser isotope separation, AVLIS, and employs visible tunable lasers such as dye lasers. 127. Another method uses liquid thermal diffusion. 9. The only significant deviation from the 235U to 238U ratio in any known natural samples occurs in Iglo, Gabon, where natural nuclear fission reactors consumed some of the 235U some 2 billion years ago, when the ratio of 235U to 238U was more akin to that of low-enriched uranium, allowing regular, light, water to act as a neutron moderator akin to the process in human-made light water reactors. The existence of such natural fission reactors, which had been theoretically predicted beforehand, was proven as the slight deviation of 235U concentration from the expected values were discovered during uranium.
Yeah.
Subsequent investigations to rule out any nefarious human action, such as
Yeah, when I want to get better, right, I choose the weakest mag because it's harder. It gives me a chance to practice.
Stable daughter nuclides, in line with the values expected for fission but deviating from the values expected for non-fission derived samples of those elements. Human exposure. A person can be exposed to uranium or its radioactive daughters, such as radon, by inhaling dust in air or by ingesting contaminated water and food. The amount of uranium in air is usually very small. However, people who work in factories that process phosphate fertilizers, live near government facilities that made or tested nuclear weapons, live or work near a modern battlefield where depleted uranium weapons have been used. 8. Or live or work near a coal-fired power plant, facilities that mine or process uranium or enrich uranium for reactor fuel, may have increased exposure to uranium. 128, 129. Houses or structures that are over uranium deposits, either natural or man-made slag deposits, may have an increased incidence of exposure to radon gas. The Occupational Safety and Health Administration, OSHA, has set the permissible exposure limit for uranium exposure in the workplace as 0.25 mg/m3 over an 8-hour workday. The National Institute for Occupational Safety and Health, NIOSH, has set a recommended exposure limit, ROL, of 0.2 mg/m3 over an 8-hour workday and a short-term limit of 0.6 mg/m3. At levels of 10 mg/m3, uranium is immediately dangerous to life and health. 130. Most ingested uranium is excreted during digestion. Only 0.5% is absorbed when insoluble forms of uranium, such as its oxide, are ingested, whereas absorption of the more soluble uranyl ion can be up to 5%. 31. However, soluble uranium compounds tend to quickly pass through the body, whereas insoluble uranium compounds, especially when inhaled by way of dust into the lungs, pose a more serious exposure hazard. After entering the bloodstream, the absorbed uranium tends to bioaccumulate and stay for many years in bone tissue because of uranium's affinity for phosphates. 31. Incorporated uranium becomes uranyl ions, which accumulate in bone, liver, kidney, and reproductive tissues. 131. Radiological and chemical toxicity of uranium combined by the fact that elements of high atomic numbers like uranium exhibit phantom or secondary radiotoxicity, though absorption of natural background gamma and X-rays and re-emission of photoelectrons, which in combination with the high affinity of uranium to the phosphate moiety of the DNA cause an increasing numbers of single and double-strand DNA breaks. 132. Uranium is not absorbed through the skin, and alpha particles released by uranium cannot penetrate the skin. Uranium can be decontaminated from steel surfaces. 133, and aquifers. 134-135. Effects and precautions. Normal functioning of the kidney, brain, liver, heart, and other systems can be affected by uranium exposure because, besides being weakly radioactive, uranium is a toxic metal. 31, 136, 137. Uranium is also a reproductive toxicant. 138, 139. Radiological effects are generally local because alpha radiation, the primary form of 238U decay, has a very short range and will not penetrate skin. Alpha radiation from inhaled uranium has been demonstrated to cause lung cancer in exposed nuclear workers. 140. While the CDC has published one study that no human cancer has been seen as a result of exposure to natural or depleted uranium. 141. Exposure to uranium and its decay products, especially radon, is a significant health threat. 142. Exposure to strontium-90, iodine 131, and other fission products is unrelated to uranium exposure, but may result from medical procedures or exposure to spent reactor fuel or fallout from nuclear weapons. 143. Although accidental inhalation exposure to a high concentration of uranium hexafluoride has resulted in human fatalities, those deaths were associated with the generation of highly toxic hydrofluoric acid and uranyl fluoride rather than with uranium itself. 144. Finely divided uranium metal presents a fire hazard because uranium is pyrophoric. Small grains will ignite spontaneously in air at room temperature. 10. Uranium metal is commonly handled with gloves as a sufficient precaution. 145. Uranium concentrate is handled and contained so as to ensure that people do not inhale or ingest it. 145. See also K65 residues. List of countries by uranium production. List of countries by uranium reserves. List of uranium projects.
Okay.
Lists of nuclear
Let's
disasters and radioactive incidents. Nuclear
yeah,
and
we're gonna take a
radiation
nap.
accidents
It's
and incidents.
yeah, it's about that time. Time for
Nuclear
the
engineering.
midday nap time.
Nuclear fuel
All right.
cycle.
So let me
Nuclear
stop
physics.
this.
Quintuple bond, earlier thought to be a 5 bond, in the molecule U2.
All right.
Thorium fuel cycle. World uranium healing. Notes.
Oh, we made it all the way to the notes. That's great. All right. So on one stream, and we'll look at the notes on the next stream, which I was kind of looking at in the.
Laughing at me.
Oh yeah. I'm coming, dear.